Hey, time to do a little calculus. Let's get into these 3-1 problems. So just at the very beginning of thinking about what a derivative is, the slope of something that is not necessarily straight. All right, so let's see. Number one, the accompanying figure shows the position versus time curve for an elevator that moves upwards a distance of 60 meters and then discharges its passengers. It's very clinical. So A, estimate the instantaneous velocity of the elevator at 10. So instantaneous velocity, we're just talking about estimating the slope. So I'm looking at the graph here at 10 seconds. I mean, it looks pretty straight. So I'm going to look for, let me just move the book over here. I'm looking at this and thinking that, so at time 10, there we are. So I just need 2 points here to estimate the slope. I mean, if I'm going to do an old school rise over run calculation, I need a couple points. So here's 2 points that look like they're on this line. All right, I'm going to take those two. You could use this one and that one. I mean, just a little rise over run. We hardly even need to do a calculation, do we? That's 20 rise over 5 run, 20 over 5, it's 4. And then the units, meters per second. Now, we're doing a position versus time graph here, so I'll just show that calculation. So rise 20 meters over 5 seconds, that's 4 meters per second. When we're doing this in just abstract math land, where we just have graphs of y versus x, we're not going to have units on here. We'll just say that slope is 4. But here, to motivate things and to give this some context, we're thinking about it with position versus time, which, hey, that totally jives with what we're doing in physics right now, too. So that's cool. So let's see. B, sketch a velocity versus time curve for the motion of the elevator for those 20 seconds. All right, so in a velocity versus time. So the velocity versus time graph is a graph of what the slope is. This is a skill. It takes some practice to get used to. My experience, having done this with many groups of students over the years, is that this is an acquired skill. You might not be instantly good at this or instantaneously good at this. So be patient. What we're trying to make a graph of what the slopes are, not like a graph that the risk or the pitfall that some students fall into is they're like, okay, so this is this steep, and they just go through this process which ends up like tracing that graph and making a copy of that. That's not what we're doing. We want to make a graph of what the slopes are. So here, for the first 2.5 seconds, the slope of this is 0. All right. So the slope is 0. And in this case, since it's position time, that means the velocity is 0. And then for the next, 15 seconds? From here to here, the slope is 4. Now, I'm not talking about something that has a slope of 4. I'm saying this is a graph of the slope, the numerical value of the slope. The slope's constant for that whole time, right? The slope all the way through here is not changing. The slope's 4, and then it's 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 4, and then finally, at 17.5 seconds, now it's 0 again. Now, if you're a good little calculus student, you might be looking at this and thinking like, well, what's up with that? You can't, I mean, are these open circles or whatever? Well, for this in physics and also in doing calculus problems of this type, we're not going to fuss about that too much. Maybe what happens is that it like swoops up here like really, really fast. It can't be vertical because then it wouldn't be a function. Or if we just want to take the easy way out, we could put an open circle there, an open circle here, or it could be closed on one of the ends, whatever. I really don't care about that. I just care about you getting those slopes. We're not going to fuss about that. All right, we're going to let something jump. You could also be thinking, if you are paying attention to reality and the world, that something can't jump from having a velocity of 0 to having a velocity of 4 without transversing all those other things in between. So maybe it would be more realistic to have it like go and come up real fast and then come down real fast. Those can't be vertical, but they can be like as close to it as you want. So whatever, really, like that's not the point of what we're doing here. So it doesn't matter to me, whatever makes you happy. All right, number 3. Excuse me. The skydiver falls vertically downward from an airplane. The accompanying figure shows the graph of the distance, s, fallen by the skydiver versus time, since leaping from the plane. Not something I'm ever going to do. I don't know about you. Not going to jump out of a plane. Use the line segment in the accompanying graph to estimate. Okay, so what they're doing here in this graph is the curvy part here, which straightens out, that is the distance that the skydiver has fallen. And then this other line, they've sketched in here a tangent line for us so that we can better approximate what the instantaneous slope is at 5. So I think for part A, that's exactly what they want us to do. So I'm going to look for a couple of nice points on that line. It looks like maybe the point, well, I guess 5, 100 is on it, right? So I'm going to use that one, and then I'm going to use that right at the end. That looks good. So that's 20, 600. So let's see, what's my rise over run? I got a rise of 500 and a run of 15. I think I got those right. 500 over 15, and that's again meters per second. So oh geez, how many 15s go into 500? Let's see. 15, so 1, so 30, 3, so 33 or something. Something like that. Let's see what the book says about that. What do they have? Oh yeah, they got about 33 too. They have like 34 rounded to the nearest. So we're approximating this. If you're just estimating using a tangent line, there's got to be a little bit of wiggle room on what the right answer is. So I'd say if you're, between, let's say, like, I don't know, 27 and 37 or ish, 27 and 40, somewhere in that range, I'd say you're good. Estimate the instantaneous speed of the skydiver at time 17.5. Now, 17.5. So right here, if you notice, it looks like it's kind of straightening out. And I don't know if any of you have ever jumped out of a plane before. Maybe. I always ask every year when I have in-person students. And sure enough, one year in one of my non-AP physics classes, I had a young woman who had indeed jumped out of a plane. And it was great to have her as a resource and tell us about what that was like. We do know that when things fall, because of the atmosphere that is sitting here near the surface of our planet, that there's air resistance, and the faster something goes, the more air resistance there is. So what happens is things reach this terminal velocity. The terminal velocity of a person falling through the atmosphere is about 100, 120 miles an hour, something like that, which is about 60 meters per second. So as her velocity here is straightening out, at 17.5 seconds, it is in fact pretty straight. So let's see if we can estimate that. I think that that looks like about maybe 3 seconds here and maybe 200 meters. So I'm just doing a little rise over run estimate. You can pick points. I don't really need to draw in a tangent line there because that's pretty flat. So let's see, what did I say? 200 rise over 3 run, something like that. So 200 meters over 3 seconds. If it was in fact that, that's about 67 meters per second. And if you want a really quick estimate of meters per second to miles an hour, just double that, and that gives you, so that's approximately, let's say approximately 120-ish. And let's see what our book said for that. What was their estimate? Oh, they got 55 meters per second. So, whatever. Close enough. Just estimating slope. All right. Oh, you know why I got that? I think that, well, I think maybe I took, my 3 seconds was a little too small for what I was looking at. Anyway, that's good. That's what we're doing. All right. So for part B where it says what appears to be happening to the speed over time, they say that it's increasing. It's true, but I would want to note that it's increasing, but it's leveling out, like it's becoming pretty straight, which means the slope is becoming pretty constant. All right, so let's do 5. Accompanying figure shows the position versus time curve of a particle moving on a straight line. So you can imagine like something moving on a number line where its position is whatever number it's at, and we record that over time. Let's see. Is a particle moving faster at time t0 or time t2? So let's see. At time t0, there's the slope, time t2. So at time t2, the slope is pretty close to 0. So it's pretty much not moving. This is like something that's staying in the same place. The position is becoming constant. If you have constant position, well, you ain't moving. Maybe you have constant position right now. I bet you do. I bet you're sitting somewhere. You're lying down, I don't know. But I bet your position is constant. So here, this thing pretty close to constant position. T0 is moving. That's enough there. The portion of the curve near the origin is horizontal. Okay, what does this tell us about the initial velocity? Well, if it's horizontal, then the initial velocity, which is the slope of that, is 0. So I'm going to say v sub 0. Actually, that might make us think that we're talking about that time, which is not quite at 0. So let's say the velocity at time equals 0 is 0 because it's horizontal. Is the particle speeding up or slowing down in the interval t0 to t1? Well, let's see what's happening with the slope. So here, I'm going from having a slope of this. The slope is how fast you're going, and then it's getting steeper. So I think from t0 to t1, because it's bending upwards, it is speeding up. When we get into things that have negative slopes, the speeding up, slowing down question becomes a little tricky at first to think about. So T1 to T2, it's slowing down because the slope is flattening out. All right, that's good. And then number 7. If a particle moves at constant velocity, what can you say about its position versus time curve? If it moves at a constant velocity, what can you say about its position time curve? If it's got a constant velocity, well, velocity is the slope of position versus time. So the position versus time then the velocity is the slope of this. So that would mean position versus time has a constant slope. And, well, you've been studying things since you were a small child that have constant slope. Things that have constant slope, otherwise known as straight lines. So, what are they? They're usually using S for position. You can use X there, whatever. In other words, the position time would be linear. If the velocity is constant, that's the same as saying that the slope of position time is constant. And if something has constant slope, it's got to be a straight line. There's no exceptions to that. All right, let's get into some algebra. Just remind you here that anything that you did and you already, you feel confident about, you know you got it right because you checked it in the back, whatever. You don't have to watch these video solutions are not required if you feel like you know what you're doing. Now, the directions for these problems are a little confusing. So if you got mixed up by the directions and you watch this first one, number 9, and you're like, oh, okay, I get what I'm supposed to do now, then pause this video and go back and try the other ones again. What we're going to do here is important. I'm going to ask you, this is the guts of a lot of the 3132 quiz, is being able to do this kind of stuff that we're going to do here. So make sure you have practice doing that. So let's just see if we understand the parts here. In number 9, I've got y equals x 2x squared, and x sub 0 is 0, and x sub 1 is 1. So for part A, find the average rate of change of y with respect to x over the interval. That's like the slope of a secant line. So my points are, maybe I'll just write underneath here, 0, comma, when I plug 0 in here I get 0, and my other point is 1, comma 2. So A is just the slope of that secant line. You probably don't need to write anything out because you're so smart. It's 2. Alrighty. Find the instantaneous rate of change of y with respect to x at the specified value of x sub 0. Okay, so time out here for a sec. Remember the definition of the derivative at a point. The point where x equals c. That definition, I'm just going to write it over here to the side, is f prime of c. F prime means the slope of f, or the derivative of f at c, is equal to the limit as x approaches c of the secant line slope. F of x minus f of c. Dang it, I didn't make my box big enough. I hate it when I do that. Over x minus c. Right? Please ignore the shortcomings of my box there. Okay, so this is just a chance to do that, I guess. So f prime of, now I'm not going to write a c here because here they want us to find the instantaneous slope, or in other words the derivative, at x sub 0. So x sub 0 is 0. So f prime of 0, that's what they're asking me to find, is the limit as x approaches, I'm not going to write a c, this is my c, 0, of f of x. Now my function is this, 2x squared minus f of 0, which is 0, over x minus 0. Well, that's about the easiest limit that you ever did, right? So I just factor out some stuff, and x cancels out. It's the limit as x approaches 0 of 2x, and of course you can just plug the 0 in there. That's not a problem. It's just 0. Okay, that's what we want to do in B. For C, find the instantaneous for an arbitrary value of x sub 0. So not for x sub 0 equals 0, but for some arbitrary value. So that's just doing the same thing as this, but not plugging something in here. So instead of calling it x sub 0, because I think that looks a little confusing, I'm just going to leave it as the c here. So we want to find what is f prime of c. Well, it's the limit as x approaches c of f of x. So whatever you put here, that's not going to change this. This is always f of x minus f of c. So let's see, that's this with c plugged in over x minus c. Okay, so I mean that's, and if you were going to rank all the problems in chapter 2, all those limit problems, this one's not really that hard, right? It's just a pretty easy factor cancel thing. Gee, I hope you got out of the mindset that, oh, it's 0 over 0, that's undefined, does not exist. That is just the worst pitfall you could fall into. If you get 0 over 0, that means time to get busy. That means it's an indeterminate form, and you have to do stuff. That is a starting point, not an ending point. Okay, so after I factored that, those cancel, and I don't think I need to write out another line. Can handle that algebra there. So now I'm going to plug in C, now that I've got rid of the 0 over 0 problem, right? These are the things, and you plug in C, C minus C, C minus C. That was causing the 0 over 0 problem. So 2 times C plus C, that's 2C, so that's 4C. So that's kind of cool. That means that you don't have to do this. If you had like a list of numbers that you wanted to find the slope at, you wouldn't have to do this every time. We just figured out, like, whatever number you want to find the slope at, this is the recipe for doing that. You just multiply that number by 4. So the slope of y equals 2x squared at some value, x value, called c, whatever, is 4c. That's how you find it. That's what we just did. All right, the average rate of change in part A is the slope of a certain secant line, and the instantaneous rate of change in part B is the slope of a certain tangent line. Sketch the graph of y equals f of x together with those two lines. All right, that's a lot of words that are asking us to do something that's fairly simple. 2x squared, that's a parabola. Oh boy, that's just the best sketch ever. And then they want us to just sketch in. So at 0, oh sorry, they want the secant line first. So the secant line here was the line that connected those 2 points that they gave us, had a slope of 2, right? And then they want the tangent line that we found the slope of in part B. So in part B, we found the tangent line at 0. So, well, I guess it's already there. It's that x-axis. So there's my tangent line, and there's my secant line. That's what they want. That's all. I can't really sketch. This is like that's the slope of like all of the possible lines. So I guess I could make a graph of the derivative, but we're not going to we'll do that soon enough. Not today. All right, cool. So that's how you do those. If you had trouble figuring out what to do with those directions, then you know what to do. Pause the video and try the other ones. I'm going to crank through these ones a little faster now. X cubed, x sub 0 is 0. That's going to be the point 0, 0. It goes with that. And x sub 1 is, oh, dang it. I'm looking at the wrong thing. X sub 0 is 1, not 0. So that'd be the point 1. 1 cubed is 1. Sorry about that mess there. Those are not no solution symbols. Those are 1s. And x sub 1 is 2. That's 2, 8. All right. That is what I need to know to be able to do part A, which is just find the slope of the secant line. 8 minus 1 over 2 minus 1 is 7. B, I want to find the instantaneous rate of change at this value. Okay, so that's f prime of 1. It's important to write out this whole thing, to write out the whole mathematical sentence. This thing is, I don't want to see like scratch work. It's time to grow up a little bit and realize that it's not just your algebra teacher asking you to show your work, and among other annoying things that the algebra teacher asks you to do. This is about communicating an idea, just the same as with any language, whether you're talking about Spanish, English, other language of your choice, coding language. You have to speak in complete sentences. or nobody knows, it's just garbage. So nobody knows what you're trying to say. So it's f prime of 1 equals the limit, as x approaches 1, of f of x minus f of 1 over x minus 1. So again, if that's moving a little fast, I know we're just getting comfortable with this, that's just the articulation of this definition for this function at c equals 1. All right, factoring that, x minus 1, x squared plus x plus 1, x minus 1, and look, there's me forgetting to do that. I forget to do that sometimes, but you know what? I always go back and add it in, and I never complain about it. All right. I guess I'm getting paid to do this, though, and you're not, so there's that. So when you plug in 1, that's 3. Okay, cool. So the instantaneous slope is 3 at that point. C, I want to do the same thing, but not plugging in 1, just leaving it as c. The limit as x approaches c, that's going to be x cubed minus, now I plug c into this, so that's just c cubed over x minus c. And, you know, it's a little trickier, but it factors the same way, right? It's still the difference of 2 cubes. Approaches c, didn't forget that time. X minus c, and it's x squared plus xc plus c squared, or x minus c. All right, and then those, not surprising, same thing cancels there. Now if I plug a c into this, I get c squared plus c times c. That's also c squared plus c squared. So c squared plus c squared plus c squared is 3c squared. Which is cool. That means I now have a recipe for finding the slope of y equals x cubed at any value of x. I just square that value and multiply by 3. That's the slope. And then D, they want our little graph. Here's the cubic function, sketch of. And let's see, my 2 points were 1, 1, and 2, 8. So there's my secant line, which had a slope of 7. And then they want the tangent line at x equals 1. Okay. Moving on to number 11. Y equals 1 over x. And my points are x sub 0 is 2. X sub 1 is 3. Part A. Let's see, that's the point 2 comma 1 half and 3 comma 1/3. Let's find the slope of the secant line. So I got 1/3 minus 1 half over 3 minus 2. That's negative 1/6. Okay. B. Want to find the slope at x sub 0. So f prime of 2. That's the limit as x approaches 2 of f of x, which is 1 over x, minus f of 2, which is 1 half, over x minus 2. There's a couple ways you can handle this. Here's my recommendation for how to do the algebra here. I would find a common denominator here. Common denominator is 2x. So let's see. The 2x, I'll show you 2 different ways to do this, and then you can choose what you like better. So 2 and this would need to be multiplied top bottom by x, and then the common denominator is 2x. and then that's all over x minus 2. Okay with that? Algebra 2 is a prerequisite for this class, so if you feel really horrible about that, and you really need to brush off your algebra skills. So, not trying to make you feel bad there, but that's just like routine algebra. So we got a common denominator. This expression is equivalent to this expression, just with a common denominator. And now, when you have a fraction you divide by something, that's the same as just like putting that on the bottom of that. So with a little bit of practice, you'd probably skip writing this step out and go straight to writing this. Right, so 2 minus x over 2x, and then you divide by this. That's just jamming that into the denominator there. In the same way as, like, if you have 1/2 over 3, that's a funny looking 3, that's the same as 1/6. That's how math works. One of the ways. You know, I wonder if my like sort of snarky sense of humor comes across as well when I'm only virtual and you don't get to see me in person. I think it's probably more charming in person, but anyway, sorry about that. If it's abrasive or whatever. But I'm really a very nice person. So 2 minus x over x minus 2. This is a thing that we're going to see sometimes, and we need to realize that these two things, when you have something minus something and then same thing but switched, that when you divide those out, you always get -1. Those are like the same number but opposite signs. For example, if you have 2 minus 5 over 5 minus 2, that's -3 over +3. And in general, if you have a minus b over b minus a, it's always going to be one is positive and one's negative version of the same number. So you're always going to get -1. So that's a thing we need to recognize, that when we divide those out, we get a -1. So that gives me a limit as x approaches 2 of -1 over 2x, and I plug in 2 and I get -1/4. So there we go. The slope, the instantaneous slope of 1 over x at 2 is -1/4. Now I want to do that same thing with just some generic value. I'm just going to leave it as c. So 1 over x minus 1 over c over x minus c. The algebra, it's exactly the same. So move a little faster. That's going to be c minus x. And I'm going to jump to that step there too. C minus x over 2c, no, xc, sorry, xc is my common denominator, times x minus c, and then a limit as x approaches c. Same thing here, c minus x, x minus c, that leaves a -1, and then my xc on the bottom, and then I plug in c there, and get -1 over c squared. So there you go. That's cool. That's just like a recipe for the slope. And if you're starting to catch on here, you're like, wait a minute, I should be doing part C first. Because if I did part C first, then to do part B, I would just have to take that number, 2, and plug it into this, right? And get -1/4. If I'm making this general recipe, why wouldn't I make the general recipe first and then use it to do that? Well, whatever. It's just more practice to do it this way. I think I approve of their order of things. So here's a sketch of y equals 1 over x. There's the part down here too, of course. And at 2 and 3, 2, 3. Here's my secant line, which has a slope of -1/6 according to our work here. And my tangent line at 2 is here. You can see it's a little bit more steep. That has a slope of -1/4. Sorry, it's a little bit messy, but you get the idea. And the last one. 12. We got y equals 1 over x squared. My x sub 0 is 1. It's going to be the point 1. Why did I put a minus sign there? It's supposed to be a comma. 1, 1. X sub 1 is 2. That's the point 1, 2, comma 1/4. All right. Slope of a secant line, 1/4 minus 1 over 2 minus 1. It looks like it's going to be negative 3/4. Part B, going to find f prime of 1. That's the limit as x approaches 1 of, let's see, f of x minus f of 1 over x minus 1. All right. Oh, I said I was going to, on the last one, I was going to do it 2 different ways. I'll do the other way on this one, and then you can apply that if you want. So the other way, instead of getting a common denominator, I can figure out, like, what would I need to multiply through on the top and the bottom here so that all of my denominators would go away. So this one is clearly just x squared. And on the last one, like here, for example, it's just the same. The thing you need to multiply the top and bottom by is the same thing as the common denominator. So here, if I multiplied this by 2x and the bottom by 2x, then 2x over x, that would just turn into a 2, because the x's would cancel out, minus, and then here 2x over 2, that would just be an x. So I get that. It just gets you to this step, of course, gets you to the same place. This is another way of thinking about it. So whichever way makes more sense to your math mind. So this one, maybe I'll just do that. I'll multiply by x squared top and bottom. So x squared times 1 over x squared is 1, minus x squared times that is that. And then on the bottom, hey, maybe your algebra instincts are like, ooh, let me distribute that. But don't. In these problems, you are going to be able to see better. We really want things in factored form. So multiplying things out, like distributing, is not a good idea because you're just going to end up having to refactor it after that so you can see what's up. So here, I'm going to factor that. And there's that thing showing up again where I have 1 minus x and x minus 1. That turns into a negative 1. And then I have 1 plus x. I haven't done the limit yet, so I still need this. Sorry about that. Those cancel into a negative 1. I got 1 plus x. And then an x squared on the bottom. And now I should be able to plug in my 1. So I got negative 1 times 1 plus 1 over 1 squared. So it looks like I'm just getting negative 2 there for the slope. All right. Now, we want to do the same thing, but for our value just generically as c. So all same algebra should feel like doing the same thing, except just plugging c in. And then what would I have to do, if I was going to do it this way, I would have to multiply the top and the bottom by x squared c squared. Alright, so let's see. When I multiply 1 over x squared times x squared c squared, the x squareds cancel out and I'm just left with c squared. And likewise there. And then here on the bottom, x squared c squared times x minus c. Don't distribute. I know you want to flex your algebra skill muscles. Resist. x minus c. All right, so same deal. Those cancel out into a negative 1. If you're wondering to yourself, OMG, how many times am I going to have to write out this limit x approaches thing? The answer, many times. So get over it and just do it. There's people who have real problems in this world. So plug in c in here. I got negative, c plus c is 2c, so it's negative 2c on the top, and then c squared times c squared, that's c to the 4th on the bottom. And I guess there's a c that could be canceled out, so maybe I'll just do that, clean that up a little bit. Negative 2 over c cubed. All right. And then d, make the sketch. So what does that look like? 1 over x squared looks kind of like 1 over x, but it hugs down to that axis a little faster, and since the x's are getting squared, it's symmetric to itself over the y-axis. In other words, it's an even function. So what do they want us to draw here? Our secant line that connects those points. That was my line that had a slope of negative 3/4, and then the tangent line at 1, which had a slope of negative 2. Ooh, not the best tangent line I've ever made in my life. Good enough for a sketch. All right.